Alrighty. Um, alright. I think we should be ready to go. Alright. Hello, Dr. B. Welcome to my analysis on the 2014 Ford Escape's 2.5 liter Duratec engine. Today we will dive into an in-depth analysis of one of the key powertrains used in the popular Ford models. This engine represents a critical part of Ford's approach to providing a balance of power, efficiency, and reliability. Before I get started with my introduction, I just wanted to clear up that before I was actually able to start recording videos of my actual Escape's engine components, I unfortunately got into an accident and currently don't have access to the car. So all the videos seen in this presentation are from YouTube and were the best I could find that accurately represent each component. All right. So to introduce the basics of the Escape's engine, we have a four-cylinder engine with an inline configuration. It delivers a robust 168 horsepower at 6,000 RPMs and 170 pound-feet of torque at 4,500 RPMs, making it a reliable choice for everyday driving in moderate low conditions. One of the significant aspects of this engine is its compression ratio of 9.7 to 1. Additionally, this engine can reach up to 6,500 RPMs, providing a spirited driving experience in a compact SUV package. It's a testament to Ford's engineering focus on creating engines that are both durable and capable of meeting a variety of consumer needs. So today's presentation will cover various subsystems of the engine, including the combustion chamber design, fuel delivery system, ignition system, valve train, and cam configuration, and intake and exhaust systems. We will also explore theoretical modifications such as the potential addition of forced induction to double the engine's power output. Understanding all of this, everything that goes into the engine's design and functionality provides insights into not only automotive engineering principles, but also the practical aspects of vehicle powertrain management and optimization. So going into the combustion chamber is where the engine's most critical processes occur, making its design vital for the overall performance and efficiency of the engine. The shape of the combustion chamber in this engine is optimized for an inline-four layout, which features compact and efficient design. The chamber is designed to maximize the surface area exposed to the flame front during combustion. This ensures more uniform flame propagation and efficient burning of the fuel-air mixture. The displacement of the engine is 2.5 liters, which means each cylinder accommodates about 625 cubic centimeters. The combustion chamber size is tailored to balance the air-fuel mixture efficiently, allowing for optimal combustion conditions that lead to better power output and reduced emissions. A key feature of this engine is the compression ratio of 9.7 to 1 that I talked about earlier. This ratio is a significant determinant of the engine's efficiency. Higher compression ratio generally enhances the engine's thermal efficiency, which leads to better fuel economy. However, it also requires careful management to avoid issues such as engine knocking. In this specific engine, the chosen compression ratio offers a good compromise between power, efficiency, and reliability, which makes it suitable for regular and leaded gasoline, which I'll talk about in the next slide. In terms of materials, though, the combustion chamber and other critical components are often constructed from alloys that can withstand high temperatures and pressures. And special coatings may also be used to reduce the wear and tear and to help manage the heat within the chamber. These materials and coatings are essential for maintaining longevity and performance of the engine under various operating conditions. The peak cylinder pressure that this engine can handle ranges from 91.6 to 114.6 ATMs, which illustrates the robustness of the combustion chamber's design. These pressures reflect the engine's capability to perform under high stress and contribute to its overall performance metrics. So with that being said, let's focus on the fuel delivery system, which plays a crucial role in the engine's performance and efficiency. The system is designed to work with regular and leaded gasoline with 87 octane rating, balancing cost effectiveness with the adequate performance of daily driving. The engine utilizes advanced multi-point fuel injection technology. This type of system allows for precise fuel metering at each cylinder, which is essential for maintaining optimal combustion. By optimizing the amount of fuel injected in its timing, the system can maximize power output while minimizing fuel consumption and emissions. This precision is achieved through systems operation at a standard pressure of approximately 58 psi or 400 kilopascals. This pressure level is ideal for ensuring efficient fuel atomization, a process where fuel is converted into fine droplets. Atomization is crucial because it enhances the mixing of fuel with air, which leads to more complete and efficient combustion. The strategic placement of fuel injectors plays a significant role in the system. Injectors are positioned to maximize the fuel atomization and to facilitate optimal. What the hell? What just happened here? Hold on. Let me go back. Sorry about that. I don't know. I don't know why my slide just did that. Where was I at? What was I talking about? We were talking about the fuel atomization and how the arrangement of the fuel atomization helps in achieving a homogeneous air-fuel mixture, which is critical for the efficient operation of the engine. Um, so, moreover, the nozzles of these injectors are designed to deliver fuel droplets that typically range from 15 to 25 microns in size. This fine droplet size further aids in improving the combustion process, as smaller droplets have a larger surface area relative to their volume, allowing for quicker and more complete burning. The fuel system is calibrated to match the engine's output, which provides a fuel flow rate that supports the engine's maximum torque of 170 pounds per feet at 4,500 RPMs. This calibration ensures that the engine delivers consistent performance under various driving conditions without sacrificing fuel efficiency. And overall, the fuel delivery system of this engine is a finely tuned mechanism that supports the engine's requirements for moderate performance and optimal fuel efficiency. It exemplifies how advanced engineering techniques can be used to meet consumer needs for both performance and everyday vehicle use. So moving forward, we have the ignition system, which is the cornerstone of the engine's ability to perform efficiency and reliability. The system is designed to ensure precise fuel ignition, which is pivotal for achieving the engine performance capabilities and fuel efficiency. This specific ignition system employs state-of-the-art electronic control with individual coil-on plug units for each cylinder. So this kind of setup can be seen on the right of the PowerPoint. I know my head might be blocking a little bit of it, but that's what these pictures are in this. The modern setup allows for direct and powerful spark delivery, which is essential for efficient combustion, especially under varying load and operational conditions. One of the key advantages of individual coil-on plug ignition is the ability to precisely control the timing of the spark. This precision allows the engine to adjust the ignition timing up to 0.1 degrees, catering to changes in engine load and RPMs. So such fine adjustments are crucial for optimizing the engine performance and reducing the likelihood of knocking, which is one of the really big goals of the ignition system. So the electronic control unit, or the ECU, plays a critical role in the system and continuously monitors various engine parameters such as speed, load, temperature, and based on all of this data, the ECU adjusts the ignition timing to ensure optimal performance and efficiency at all times. The capability is vital for maintaining consistent power output and reducing fuel consumption. So the design of the ignition system contributes significantly to reducing misfires, which I was kind of talking a little bit about earlier. Misfires can lead to unburned fuel escaping into the exhaust, increasing emissions and decreasing fuel economy. By ensuring a reliable and powerful spark, the system helps maintain a clean and efficient combustion process. Additionally, the spark plugs used in the engine have a specific gap of 0.052 inches or 1.32 millimeters. This gap is critical for creating an optimal spark that ignites the fuel-air mixture effectively and maximizing combustion efficiency. This gap helps in ensuring the spark has enough energy to ignite the mixture efficiently. And the system's robustness allows it to handle engine speeds of up to 6,500 RPMs without loss of ignition reliability. This high RPM capability is particularly important for maintaining performance during demanding driving conditions. And in summary, the ignition system of the Durtech engine is a finely tuned component that integrates advanced technology and engineering to support the engine's efficiency and power output. Its design and operation are critical for ensuring that the engine meets its performance and efficiency targets, making it a key factor in the overall success of the engineering design. So with that being said, it's time to turn our attention to the valve train and camshaft. These are pivotal in enhancing the engine's performance. The engine is equipped with a dual overhead camshaft configuration. This design allows for better control and timing of the valve operations, which is crucial for optimizing airflow throughout the engines, especially at high speeds. The DOHC setup in this engine features 4 valves per cylinder, 2 for the intake and 2 for the exhaust. This arrangement significantly improves the engine's ability to breathe by increasing the volume of air intake and the efficiency of exhaust gases expulsion. More air coming in and going out means better combustion, and consequently, higher efficiency and power output. A key component of the system is the camshafts, which are driven by a timing chain. Timing chains are preferred over belts in many modern engines due to their durability and low maintenance. In the case of this Duratec engine, the timing chain is designed to last over 150,000 miles under normal driving conditions, which speaks to the engine's reliability and the reduced need for frequent maintenance. One thing I can say is that, yeah, my car definitely did not have a lot of maintenance needed for it, and I probably had about 120,000 miles on it before I got into the accident, and it was running great. Honestly, I'm so mad that I got into the accident because it was a good car. And as much as I was not an SUV guy, I mean, I really liked it. But going back to the valve train cab, this engine employs advanced variable valve timing technology, or VVT, which allows the timing of the valve opening and closing to be adjusted dynamically. This adaptability is crucial for balancing power output and fuel efficiency across different driving conditions. In this engine, VVT can adjust the intake valve's timing over a range of 30 degrees. This flexibility helps in reducing emissions and improving fuel economy. And the camshafts themselves are engineered with precision, operating with a lift of approximately 0.25 inches or 6.35 millimeters, and a duration that optimizes airflow at medium to high RPMs. This specific lift and duration ensure that the valves open sufficiently and for the right amount of time to maximize air intake and exhaust without creating undue engine strain. In summary, the valve train and camshaft design embodies sophisticated engineering that significantly enhances engine performance. By allowing better airflow, reducing emissions, and improving fuel efficiency, these systems demonstrate how advanced mechanical design can meet the demands of modern vehicle engines. So here we go. So right here, I have a video. This is just like a quick video of the DHOC. And, this car, So that's really I just kind of wanted to give you a quick look, just because I couldn't do it myself. I kind of just wanted to give you a good like what the DHOC actually looks like in the Ford Escape. So that was kind of the whole point of that video. But moving forward, we had the intake and exhaust systems. Both are crucial for the engine performance and environmental compliance. So, starting with the intake system is specifically designed to maximize efficiency. It features a careful, calibrated air filter and an intake manifold that optimizes airflow with minimal resistance. At full throttle, the system can manage an airflow rate of about 250 cubic feet per minute. This high flow rate ensures that enough air is supplied to the combustion chambers to support efficient fuel combustion at varying speeds and loads. And moving on to the exhaust system, which plays a pivotal role in emissions control. This system incorporates a high efficiency catalytic converter that converts over 90% of harmful emissions into less harmful gases. This is very important for meeting stringent environment regulations and maintaining good air quality. And additionally, the exhaust system includes oxygen sensors that monitor the exhaust gases. These sensors ensure that the air-fuel mixture remains close to the stoichiometric ratio of 14.7 to 1, which is the ideal ratio for optimal combustion and efficient fuel usage. Maintaining this ratio helps in minimizing unburned fuel, thus reducing emissions further. Another aspect of the exhaust system is the management of back pressure. It is maintained below 1.5 psi, which is critical for efficient exhaust gas evacuation, and proper back pressure management ensures that the engine does not lose power and continues to generate torque effectively, especially at lower engine speeds. So both the intake and exhaust systems are tuned not only for performance and efficiency, but also for noise reduction. This tuning addresses the needs of the general consumer market, which prefers vehicles that offer a balance of performance, efficiency, and quiet operation. In summary, the intake and exhaust systems of this engine showcase advanced engineering designed to optimize performance, reduce emissions, and cater to the consumer preference. and further reflect everything that Ford kind of works for with environmental responsibility and customer satisfaction. Um, so with that being said, let's go into the boost pressure calculations. So before I get into the actual math, some assumptions were made. Isentropic compression of the intake charge by the supercharger, because my engine is naturally aspirated. There was no intercooler used, so the temperature rise due to compression must be considered. Er, Engine's original power output is approximately 168 horsepower at 6,000 RPM. So the basic principle here is that power output of an engine is proportional to the mass flow rate of, of air it consumes, assuming fuel delivery can be matched accordingly. Doubling the power output requires doubling the mass flow rate of air into the engine. So I have all my variables listed out on the left right here, and the original boost equation was talked about in the lecture. So after I have all this, I did the isentropic relation for pressure and temperature and doubled pressure for doubling power. And then I calculated final temperature sub value. Let me see if I can move myself over here. I can't. So you, all right, here we go. Perfect. So yeah, so then I calculated the final temperature and subbed the values into the isentropic equation, as you can see here. And I got T2 equals 375.48. So using this number, I was able to. First, I gotta move myself over. Come on, come on, come on. There we go. So then I was able to actually calculate the required boost pressure needed to double the power. So as we can see, I had an ambient pressure of 101.325 kilopascals. And then, so then for my P2, all I had to do was double that and got 202.65 kilopascals. So the boost pressure is just P2 minus P1, which is 101.325 kilopascals, which is basically just P1. So I got 14.7 psi. So 14.7. So I concluded that 14.7 psi is the required boost pressure to double the engine power production. So yeah, with that being said, the calculated more of just an explanation, pretty much everything I just said. But going further off that, this indicates that this is additional pressure above atmospheric levels is needed to be provided by a supercharger to approximately double the engine's horsepower. This boost effectively increases the air density entering the engine, allowing for greater air mass per cycle, which, when matched with the correct fuel ratio, significantly enhances the engine's power output. And in conclusion, the detailed examination of the Durtex engine systems and component underscores its sophisticated design and Ford's dedication to innovation in automotive technology. This engine not only meets the demands of modern driving, but also sets a benchmark for future developments in internal combustion engine technology. So after this, I have a couple of videos for you. So here's a strip down of the engine. I thought this was just like really good to show you. Obviously, because I can't do it myself. Obviously, I don't have the car, but just get an overall better look at what the engine looks like and how all of these components kind of come together and how it fits and how it works. But I'll let you watch. Yeah, that was just a nice quick video though. I thought that was really good, really interesting video that I'm sure that you'll like. I wish I could have taken it myself, and I wish I could have done more videos of me actually in it, but obviously accidents happen. But I got one more video for you too as well. If this one ever wants to stop. So this one, this is some guy just with a 2.5 liter engine, just going from 0 to 60. One thing I can say about this car when I had it is that this thing did pack a punch. This thing, I mean, it might be, but this thing, oh, you can say here you go, 0 to 60 in about 20 seconds of this, about 10 seconds. There you go. Those RPMs. But yeah, I thought those were some pretty interesting videos. Once again, I wish I could have got more for you. But obviously accidents happen. But yeah, with that being said, I have some references here, and there we go. And so that, yeah, that's my analysis on the 2.5 liter uh, Duratec engine found in the 2014 Ford Escape. So thank you very much, and I hope you have a great summer, Dr. P. Thank you for being an amazing professor. Brought up there with my favorites here. Um, wish you the best of luck. Thank you so much. Have a good one.